That's a long title. Thank you, Ashley. I'm Bhagya Subrine. I am a recent graduate from Purdue University. And first of all, let me thank the organizers for giving me this opportunity to speak at this conference. So today I'll be speaking about a part of my thesis work, but I'll be also speaking about another part of my thesis work as and when I will be describing this really exotic transient called Scary Barbie. Which is an anomaly which was detected from the ZTF survey, and how we ended up finding these rare gems in the current ZTF survey data, and how do we plan to apply these for the upcoming LSSD survey. All right. So this is the Rare Gems in Big Data conference. So we all know that LSSD is going to be clearly at a scale where the data stream is going to be so huge, and it's not clearly at a scale which is handleable by humans. So we need, and as from previous talks, it's already clearly understood that we need automated systems which are able to predict, identify, and prioritize transients as well as follow them up. So it is a great, excellent platform where I could introduce this effort which we are leading at Purdue University called REFIT, which stands for Recommender Engine for Intelligent Transient Tracking. So what REFIT does is it's an automated artificial intelligence systems that can identify, predict the evolution of transients, and provide recommendations to observing agents to follow these transients up. So here I'm showing a flow chart of how REFIT works. So currently this is a prototype which is run on ZTF survey, but we plan to extend this it is in preparation for the LSST survey. So it ingests data from the ZTF All-Sky survey through the Antares data broker. And then the second part is where all the predictions of the evolution of the transient as well as the prioritization happens. And then the next step is where you send out recommendations for follow-up of transients to a suite of observing agents. And these could be anywhere from mid-size aperture telescopes to large facilities. And then the data is acquired on these transients, and it is fed back to the loop of a REFIT ecosystem where it is used for better and accurate, more better predictions or recommendations. Now, I just have to mention that this is a part of the REFIT program is also a part of the Supernova Early Warning System collaboration, which is going to coordinate different worldwide observing facilities for the next galactic supernovae. So the main two focus of this program is A, we need to find interesting targets from these data deluge. It can mean that we need to find gems, or maybe we need to find rarest gems. The second one is to augment data from which can complement these alert streams. So you find a target, but then the survey data itself might not be enough for doing science on those targets. So it coordinates observing agents to get data or augment data from these for these alert stream data. So part of my thesis work is also related to how can we how can we motivate the predictions of these transients just from light curves by fitting theoretical models in real time. So the question that we are asking is, can we make predictive forecasts based on the underlying physics of these transients itself? And earlier, Josh mentioned about how much information we can retrieve from just images of the galaxies. There is a whole ton of information that you can do from the light curves of these transients from these data streams. And here comes an example. So here what I'm showing is how a core collapse supernovae evolves in real time. And what you're seeing as those lines are hydrodynamical models fitted using statistical sampling methods. And at each epoch, so it's a gap of 10 epochs, it is evolving. Every epoch, physical parameters associated with this explosion is derived. And this can be used as a powerful technique for detecting anomalies from all-sky surveys. And I'll show how. So what are the benefits of doing this kind of real-time characterization? Is first, depending upon what your gems are, so depending upon what your scientific case is, just from a data stream, you're able to extract a whole lot of information about the physical parameter spaces of these transients. And that can be gems for some communities. So suddenly you're sensitive to this internal information, which is not available with data-driven approaches. Second, to the part where you can augment things, real-time characterization can be a powerful tool to identify epochs where observations need to be followed up, especially in this case where the physics blind fit is not doing a good job in understanding or predicting the evolution of the transient. Now, the part where is interest of my talk is an anomaly. So I will demonstrate how anomaly detection can be a part of this real-time characterization. So we have heard anomaly detection in this conference right from the beginning. So the traditional way in which anomaly is detected is using data-driven approaches where you train a model based on previously observed events, and then newly observed events which do not or which deviate from that model are occupies spaces in the feature space plot which are different from the others. So you can tag them as anomalies. But that even though it's a very powerful way of identifying anomalies, you don't understand about the physics of the systems involved in these anomalies itself. And I would like to highlight the work of Braden Garrison, who's an undergrad, who's part of the refit team. He uses machine learning algorithms to develop methods and tools for classification, data-driven modeling, as well as rapid theoretical inference from refit. So this is different from theoretically driven anomaly detection, where you fit a suite of theoretical models in real time for transients, and then you are suddenly sensitive to things that do not fit well at all. Like if you fit a suite of theoretical models to data streams, you're suddenly going to be sensitive to things that do not fit anything at all, and that can be immediately flagged as anomaly, or that can be immediately flagged as anomaly. So these include a different variety of events, for example, long duration events, rebrightening events, things with precursor activities. And bringing back the focus of the talk, which is called Scary Barbie, this is a transient which was discovered with the refit team. It was an anomaly which was flagged by the refit team because of its long duration rise time. And I would tell you why this is called Barbie, because its internal name was ZTF20ABRBEIE, and we were dyslexic, and then we were just like, it's called Barbie, and the internal name Ho stood on. So why it became scary is because of its extreme characteristics. All right, so first, it's a long duration event, so it's over 1,000 observer frame days. It's still evolving as I'm speaking in this room. The second is its extreme energetics. It's orders of magnitude luminous than any known supernovae, and its lower limit is about 10 to the power 43. So here I'm showing you a comparison between Barbie and other transients, including TDEs, AGNs, and supernovae. The absolute magnitude reaches the order of a quasar, which is about -26, but there are other features in the light curve as well as spectra, which do not comply with what a quasar would look like. The light curve is extremely smooth in its rise as well as decline. We followed this up. So, and comparing this with other transients, it has a narrow hydrogen or Balmer lines, but it is missing the oxygen doublet, which is seen in commonly seen in other QSOs, TDEs, as well as supernovae. Now, you would think that if there is so much energy and luminosity emitted, it would be something where a system can actively convert matter into energy. And we thought it could be something to do with the TDE. So we modeled the available photometry with the TDE candidate. And extreme parameters for luminosity as well as energy gives you extreme parameters for the TDE models. So the scenario that we derived from the modeling was that it was a 14 solar mass of a star, which was being stripped apart by a supermassive black hole of the orders of 10 to the power 8 solar masses. Now, this is extreme within the TDE community because there's a sharp decrease in the TDEs, which are observed with black holes of the order 10 to the power 8. And the typical range of solar masses of stars, which are being stripped apart, are 1 to 2 solar masses. So these parameters are really extreme. Now, the even intriguing part of this puzzle is that you would expect the supermassive black hole to be hosted by a host galaxy, but we did not find any host galaxy yet, which is detected yet at the location of Scary Barbie. So this is still an ongoing puzzle and an open question, and we need future observations for conclusively determining what the physical interpretation of the system is. And this is my last slide, not second last slide, and I just wanted to wrap up with the focus on how we are going in the direction of finding these rare gems in big data is where earlier Michael talked about likelihood-free inference. So fitting a suite of theoretical models in real time with likelihood-free inferences can only take about seconds of time, and that can be used as a powerful tool for detecting anomalies. And we are going to be sensitive to these question marks in this plot, which is going to be the spaces which we will be probably discovering with LSST. And that's the summary, because I asked DALL-E how scary Barbie in space would look like, and it gave me this. So thank you so much.